When we add a catalyst to a system where a chemical reaction is taking place, if we pick the right catalyst, it can increase the rate of reaction. So we're looking at a case where at 300 Kelvin, the rate of reaction increases a factor of 100 by adding a catalyst. And it does this by reducing the activation energy, keeping everything else about the reaction constant, the same order reaction, the same pre-exponential factor. And the question is, what activation energy do we have when the catalyst is present if the uncatalyzed activation energy is 20 kcals per mole? I'm going to call rate 1 the uncatalyzed rate, and then rate 2 is the catalyzed rate. And then we know that rate 2 over rate 1 is equal to 100. We know the activation energy for the uncatalyzed reaction, E1, is 20 kcals per mole. The rate is going to be the pre-exponential factor, the activation energy, and then some concentration dependence, so some function of concentration, same K0, E1 now over RT, and the exact same concentration dependence, but that ratio is equal to 100, so these cancel, and we have e to the minus E2 plus E1 over RT is equal to 100. So we can take the log of both sides, minus E2 plus E1 over R. So let's put in R. Since this is kcals, I'm going to write this as calories, so I can use 1.98 calories per mole Kelvin, the gas constant. Temperature 300 Kelvin, absolute temperature. Remember, these E's now, I'm going to write them 20,000 calories per mole. And the log of 100, 4.605. And I know E1, so I can solve for E2. Let's do it this way. It's equals, and then bringing E1 the other side, minus E1, so that's minus 20,000. Or E2 is equal to plus 20,000 minus multiplying these numbers out. This is 2735. So we calculate E2 and I write it as kcals per mole. And then we might consider this at best two significant figures because of the accuracy of the starting data. You can see we have a lower activation energy, which results in a higher rate of reaction.